So hopefully now at this point we know how to find the molar mass. We can actually use that to give us the number of grams if we know the moles, or vice versa, give us the number of moles if we know the grams. So we did this way back when we were dealing with just elements. Now we're going to kind of take a look at it in terms of compounds. And if you remember, we had a little diagram, something like this, where moles is in the middle. Both the top and the bottom are essentially the same process, just the top is for compounds, the bottom is what we did in the past with elements. But if we're going from moles to molecules or formula units, we're going to multiply by Avogadro's number. If we're going from formula units or molecules to moles, we're going to divide by Avogadro's number. If we are going from grams to moles, we're going to divide by the molar mass that we learned how to find. And if we're going to moles to grams, we're going to multiply by the molar mass. So those are my four situations. I could go all the way from one side to the other. If I had to go from mass to number of particles, I could take mass times the molar mass to get to moles, then take moles times Avogadro's to get to the number of particles. Or if I want to know how many grams are in a certain number of particles, I can divide that number by Avogadro and then times it by the molar mass. I hope I said divide by molar mass, then times if I'm going from mass to particles. But you get it if it's in the denominator. Hopefully you get it. If it's in the denominator, you know to divide. So if I'm multiplying by 1 over something, in actuality, I'm dividing. So we've essentially done this in the past. Does anybody have any questions on that chart? Hopefully that rings a bell to us, because we're going to do it here in sample problem H with 2.50 moles of oxygen gas. The tricky part about this one is you might be tempted to say O for oxygen gas. You guys know what the actual formula for oxygen gas would be? Remember, oxygen is a diatomic molecule, so it naturally comes as O2. So we have to be careful if they want elemental oxygen or if they want molecular oxygen, which is oxygen gas. We're going to write down the number that we're given, 2.50 moles. This background's glitching on me, so I'm going to pause it. And 2.50 moles, the mass in grams in a mole is what we're trying to find. So according to our table, when I'm going from moles to grams, I need to do what? If I'm going from moles to grams, I need to multiply by molar mass. So I actually set it up wrong here. I don't know what I'm thinking. Put 1 mole on the top. We need to multiply by the molar mass. So from our previous homework, how am I going to get the molar mass of O2? Where can I find that? And where can I find the molar mass of oxygen? Remember? Where do I get that information? Yeah, on the periodic table, right? So, what's oxygen's molar mass? 16. And we have 2 of them. So we're going to take 32 grams per 1 mole. And this is for oxygen. Therefore, my moles cancel out, and I'm left with 2.50 times 32. 32 times 2 is 64. Add a half is 16, so it should be 80. If anyone wants to verify me on that, 80 grams of O2 and 2.5 moles. We good with that? Going from moles to grams? Is it 80? Cool. So let's try a more involved problem here. We've got ibuprofen, which is C13H18O2. Many pain relievers have this. Molar mass, they give it to us, but we could find it if we wanted to. We could take, C, H, and O. Carbon has a molar mass of 12, and there's 13 of them. Hydrogen has a molar mass of 1, and there's 18. Oxygen has a molar mass of 16, and there's 2 of them. $12 times 13, that's what, 166? No, 156. 1 times 18 and 32. So then 206, look at that. Adds up to 206. So that's how I would find the molar mass if I was asked to, but I wasn't. If the tablets in the bottle contain 33 grams of ibuprofen, how many moles of ibuprofen are in the bottle? So 33 grams of ibuprofen. Remember my chart, if I want to go from grams to moles, what do I want to do? I want to grams to moles. Looks like I need to multiply or divide by the molar mass. Oh yeah, I can try this. So multiply by the reciprocal side. So going from grams to moles, I'm going to need to divide. Does that make sense? I know it has the times there, but I get it. If I were to draw that myself, I would just put a divide sign, but I'm using the book's picture there. So 33 grams per mole. So I have to divide by that 206. I'm only going to have 2 sig figs in the end because they only give me 2 sig figs in 33. So 33 divided by 206. I want to say it's 0.16. If I remember correctly, 0.16 moles. Does that make sense? 33 divided by 206. And that gets me in the moles. So how many molecules? I can just keep it going. So this next question asks me how many molecules. So to get molecules, if I have moles, this should be review. If I have moles, number of molecules is just times Avogadro's number. So I'm going to take that number that I just got, the 0.16, times Avogadro's number. It's unfortunate that molecules has the same first 3 letters as mole, but 6.02 times 10 to the 23rd molecules per mole. Moles cancel out. And I'm left with, can't do that one in my head. Somebody want to take 0.16 times so 0.16 times 6.02 E23. I get 9.6 times 10 to the 22nd molecules. So this was the answer to the first question. This is the answer to the second question. And they ask us one more. Any questions so far? So the next one, we need to think about it in terms of the number of moles of carbon in this compound. So if we already know that if I have 33 grams of ibuprofen, I have 0.16 moles. So that means I have 0.16 moles of C13H18O2. How can I determine how many moles of carbon I have? So how many moles of carbon are in a mole of that stuff? If it helps, think of this as a kit or a box. Ibuprofen is like a molecule, it's a set. And in that set, I have 13 carbons, 18 hydrogens, and 2 oxygens. So if I have 1 mole or 1 set of ibuprofen, that means I have 13 carbons, right, in my kit. So if I only have 0.16 moles, I'm going to have a fraction. I'm going to have 0.16 times 13 is only 2.08. So I have a fraction of that 13 moles of carbon. Makes sense. If I have 0.16 moles of the whole thing, I only have 2.08 moles of carbon. Or I have 2.08 full moles of carbon. Just like if I have 1 mole of ibuprofen, I've got 13 moles of carbon. But that's not what they're asking for. They're not asking for moles. They're asking for grams. So to convert moles of carbon to grams of carbon, I know that there are 12 grams in every 1 mole. So 2.08 times 12 is 299 or 300 roughly. That doesn't make any sense. Yeah, 300 is way too high. The actual answer is 24 or 25 if we round up grams, which is a fraction of the 33. I accidentally multiplied by 12 twice instead of once. So that's my answer for the mass of grams of carbon. But there's another way we can figure it out. We can actually use the percentages based on the numbers we found up here. So if you notice, we've got 3 elements out of a total. So each one contributes some to that 206. So what I can do is I can say carbon is 156 out of 206. Hydrogen is 18 out of 206. And oxygen is 16 out of 206. I can find a percentage for each of those. So 156 out of 206 is calculate that. %, and then 18 out of 206 is 9%, or 8.7 to be precise there. And then 16 out of 206 is 8%. So those all add up to 100. No, something's. Oh, I did 16 instead of 32. Man, I'm messing up all over the place today. We haven't done math and calculations in a little while. So 32 out of 206 should then be 16%, which should add up. Like I said, this is closer to 8%. It adds up to about 100. Anyway, all that to say, carbon makes up 76% of the whole molecule. So if I have 33 grams, Does 25 grams sound to be about 76% of 33? So what I can do is I can take 0.76 times 33, and I get 25. So it's about 25 grams. So see how we can break it down by percentages, and then, I know that was a lot, but we'll get some practice with it, especially since the next slide tells us about percentage composition, which we're going to find in tonight's homework. Percent composition is essentially the mass of the element in the sample divided by the mass of the sample. We can actually use the molar mass of the element, just how we did in that problem up here. We can use the molar mass of the element divided by the molar mass of the compound. But make sure you're doing the mass of the element in the compound. So I did have to multiply the carbon by 13 first. I had to multiply the 1 by 18 first. And I had to multiply the 16 by 2 first. So I kind of call that the contribution. How much does each one contribute to the mass of the element? And that's just the percentage of the mass of the element in a mole of the compound versus the molar mass of the compound. And that was my percent composition. I said this compound is made of 76% carbon, 9% hydrogen, and 16% oxygen. Here's some other examples. You can see the difference between iron 3 oxide and iron 2 oxide. Let's take a look at how we got those numbers, because I think we need to see a little bit more of this. So iron 2 oxide, Fe2O3, it's crazy background turned off. Fe2O3, we've got Fe and O. So iron is, can someone tell me the molar mass of iron real quick? I know oxygen 16. And this one, 55 or 56. 56. And there's 2. And this one, so 56, there's 1. There's 1. So the total molar mass of FeO would be 56 plus 16, which is 72. The molar mass of Fe2O3 would be 56 times 2, which is 112. And 16 times 3 is 48. So 112 plus 48 gives me 160. So if I take 112 out of 160, you said 112 out of 160? 112 divided by 160? Or did you subtract? Did you subtract it? If we take 112 divided by 160, you should get 0.7, so about 69.9%, and then 48 out of divided by divided by 160 is about 30%, 0.3. Over there, 56 divided by 72 is 77.7, and then the rest is obviously getting 22.3, but we can take 16 divided by 72, and I get 22.2. Note the rounding error is going to mess us up a little bit, but as long as our sig figs are all in order, we should be good. But hopefully you can kind of see where those numbers came from. They're just not pulled out of thin air. We're going to skip this for now because we're going to talk about empirical formula next section. Well, let's do one last sample problem finding the percent composition of copper 1 sulfide. So copper and sulfur. I know sulfur is 32 grams per mole. What's copper's molar mass? 64? Either guys able to tell me copper? 63. And we'll round it up to 64. And with copper 1 sulfide, there's Cu2S. So we have to multiply that by 2, multiply that by 1. So it's 128 grams per mole and 32 grams per mole, giving me a total of, that one's 160, right? So 128 out of the total and 32 out of the total. And it should be 80% for 128, so 0.8, or 80%, and then 0.2 or 20%. Notice those need to add up to 100. So this is my answer. I'm saying copper is 80% and sulfur makes up 20% of that compound. So I have a homework assignment. We can look at one together, but that's all I have for the new stuff today.